It's good. Can you guys hear me? Okay, cool. All right, running late, why don't we start? Good afternoon, everyone. My name is Wei Zhang. I work for Facebook infrastructure storage team. We're going to, the topic we're presenting today is exploring Lightning JBoF configurations for different use cases. So if you follow the OCP storage track, you must be familiar with the concept of JBoF, right? So Facebook developed the Lightning system a while back, and then we contributed the software, the hardware specification to OCP. And currently, Lightning is in our production environment. It's in our data center, serving live traffic of the users, and we have multiple applications running on the Lightning platform. In this talk, I'm going to explore the different configurations of the Lightning platform based on our experience learned from the production environment, right? So one thing you have to realize is different applications has different requirements, and to be able to use the hardware efficiently, we'll have to be just a little bit smart on how we actually use the hardware system. So we feel we want to share these findings with the greater OCP community so that people who actually want to migrate to Lightning will be able to take advantage of these findings, right? Let's work with the... Okay, so just to start with, let's revisit what is the Lightning JBoF, right? It's just a bunch of flash platform. It's an NVMe-based storage platform using the NVMe SSDs. It does have a top tray here, a top tray, a bottom tray, and this is really inherited from the Knox chassis before, right? These two trays are sort of working independently. They're not actually associated with each other. And the platform support both M.2 SSDs and U.2 SSDs, and it does support the PCIe hot plug. One thing to note is this is a storage chassis, right? You have to connect a compute node to be able to run your software stack. This is what we refer here as a head node. So you have to connect a PCIe retimer card on the head nodes and then connect through a PCIe cable. Okay, so as I mentioned just now, right, one thing we realized when we deploy Lightning is the flash workloads that trying to migrate to the platform is actually quite different. There are, our primary use case for Lightning is to use it as a block storage server. This is basically a storage appliance to export the flash capacity flexibly to the compute clients over the network, right? The protocol here you can use is NVMe or TCP if you prefer NVMe-based protocol, or you can use just a generic block service like a network block device, NBD. And what's common about these software stacks is they're lightweight on CPUs, right? If you use a direct block I/O, they're also lightweight on memory as well, right? Because they're not caching anything in the RAM. Here, what it means is with this kind of a software stack, you actually can support a lot of flash capacities, which basically you can set up all the SSDs, contribute, basically belongs to one head node. There's another type of applications like the database servers, like the RocksDB servers. They are actually very much compute intensive, and they use a lot of memory. In this case, it's very hard to actually consume the full capacity of one chassis, right? So you got to be flexible to be able to connect them to multiple head nodes in order to consume the full capacity. And this is, I have one chart here just to tell you the difference. This is like a CPU utilization between the two different type of servers I captured during the day, during a full day span, right? So this is a normalized CPU utilization. So if you use the block storage server as the baseline, you could realize for the database server, they actually consume at least more than 3x of the CPU. but note that this is like a normalized chart. But the key takeaway here is basically what I just said, right? If you're running a database server, they are more CPU intensive. They can only consume less flash flash capacity. So how do we deal with one Lightning platform, right? Fortunately, if you're smart enough about how you configure the PCIe switch we use, you actually can manage the flash pool and be able to connect more head nodes to the system, be able to use the capacity flexibly. And to be able to understand that, we'll go through, let's revisit the Lightning architecture, right? This is, here is a one Lightning tree. Remember, there's two trees here. This is one tree with a PCIe switch. What we have here is we have 8x4 upstream ports connects to the server, and then we have 30 downstream ports connects to the drive, which is M.2 drive in this case. And also we can have 15 downstream ports connected to the U.2 drives. And there's also another concept called switch partitioning, right? So this is a one physical switch, but you can create multiple switch partitions within the one physical switch. And by the way, this is what we're using, the microchip switch. It's a fan-out switch with 96 ports. But you can create multiple switch partitions, and then each partition basically operates as independent of PCIe switch. It complies with the PCIe spec. And you can manage you can create one upstream port for any of the partition, and then multiple downstream ports belongs to that same partition, right? And this is how we actually managed the pool of flash in Lightning to be able to assign them to freely to different head nodes. And here is how. So this is one configuration we use to use Lightning as a block storage server, and this is actually our primary use case in our data center. And you can see here we only create, we have two partitions, but we only use one partition here, right? And this partition, we have assigned all the SSDs to this one partition, and then we only connect one head nodes to the by16 upstream lane. And this is, again, because the software stack running here is lightweight, and then they're able to consume all the flash capacities within the chassis. This is another configuration we considered. This is, again, tied back to the database server, RocksDB server I mentioned just now. With this, we create 4 partitions within the PCIe switch. And then we assign 8 drives or 6 drives to each of these partitions. And with this, we basically carve out the Lightning pool, the pool of flash storage, and be able to assign them to different servers. And you may ask, right, this is very similar to like a local storage setup, right? So why the heck we need a switch in the middle? We can maybe just connect the 8 SSD to the server, right? And this is tied to another switch feature I will mention later. It's called dynamic partitioning. And you actually, this is one configuration, but it don't have to be static, right? You can actually move these SSD around based on the head node's needs, right? You may run a different, more intensive software stack here. Then you can maybe trim off the SSDs, move the SSD to other head nodes connected to the chassis. This is called port migrations or dynamic migrations. And this is one advantage of using a pooled storage and be able to allocate them flexibly rather than using a local flash setup that you will be stuck with those flash capacities and won't be able to utilize them at its full capacity. Okay, another challenge we deal with in our production environment is platform availability, right? By this means is like what is the requirements, like what is the application requirements on how what the platform downtime, right? How can you basically there's different kinds of applications. More enterprise-oriented, mission-critical applications would prefer the platform keep going without any downtime, even doing software upgrades and doing a full repair. And there are also cloud applications that basically concede the system can go down, right? So there's a trade-off how you actually set up the system to be able to perform at the platform availability that they require. So to that aspect, Lightning itself indeed is represent a large failure domain, right? So for example, if you connect 2 terabytes M.2 SSDs to the system, it represents 60 terabytes of flash capacity. And so if the head node goes down, it brings down the 60 terabytes capacity entirely, right? You won't be able to access the data at all. And one thing to note is the failure, is not really, it's really a broader sense, right? It doesn't necessarily to be a hardware failure, like the head node has failed, or CPU has failed. It could be also a system downtime when you do a firmware upgrades, when you do a kernel upgrades. The system needs to reboot, and also the data is not available in that case if you don't have anything handle the failover. So the other thing I want to mention is in our data center environments, in our applications, the data recovery should head node goes down is actually really non-trivial. There are different cases to recover, and applications will backup. They have multiple regions backup. In this case, to load the data into this region will cost network bandwidth. And in other cases, if you do an encoding scheme, you will need the compute resource to actually recover the data stored on this node, right? So to be able to get smart and keep the platform going when there's such a downtime, we need a failover capability. And this is, again, the PCIe switch can provide a functionality like this. Okay, to be able to understand what's the impact, I actually did some analysis on our fleet. This is like the head node, the title here is called head node reboots. It's basically how many head nodes goes down within a day, right? So this is roughly a 6 months span of time. And then I think it's roughly around 1,000 head nodes in the production environment. What we can conclude is, on average, in this setting, there's about 8 head nodes going to reboot, experience a downtime in our system, which means if you have 60 terabytes of flash on each tray, then you're experiencing like almost half terabytes data available on a daily basis. So what this means is keep the platform going in such events is really critical, right? So you don't have to refetch the data from another region or recreate the data from the encoding scheme. Okay, so fortunately, if you do some clever configurations, you can make use of the PCIe switch to create a failover situation. And this, again, ties to a feature called dynamic partitioning. And in the normal PCIe switch, conventional PCIe switch, there's a P2P bridge functionality, which is have a one-to-one mapping with the physical ports that's connecting to the end device. And this is a conventional switch, and unfortunately, the switch we use actually, the microchip switch has a feature called dynamic partitioning, which essentially create a mapping layer between the P2P functionality and also the end ports. Basically, they break the relationship and be able to use this mapping layer to migrate this physical port to one of the P2P ports that is configured in the different partitions. What this means, it works like a hot plug event. What this means is for example, like today, at this point, the SSD is connected to this P2P. You could issue a MRPC command to unband this SSD from this partition, right? That looks like a hot remove event to the host connecting here. And then you can issue another band event to this partition. It will actually migrate this SSD to this partition. And the host connect to this partition, see this as a hot plug, hot add event, will basically take over the SSD and have the data available from this host. And okay, so with this feature, we can create a head node failover case. So essentially, we have, remember I mentioned there's top trace and bottom trace on the Lightning chassis. And in the previous block server case, we basically connect one head node to each of the tray, right? And with to be able to utilize the failover feature, we can cross connect the two head nodes to the other tray. And which this means we are adding a retimer card to each of the head nodes, and then adding another cable connecting to the other upstream ports in that tray. And then on the switch configuration side, we create two partitions. One active partition basically bound with 30 M.2 SSDs, and then one passive partition to be bound on the SSDs when the other head node failed, right? When the paired head nodes failed. It looks more clear from a picture here. If you look at this, this is the normal running state in a failover setup. The bolded line here is the active line. The thick line here is the active line. So the live head nodes connects to the top tree, connecting to all these SSDs. And then there's a head node on the right-hand side connected to the bottom tree. And these are the normal running scenario, right? And this cable here and this cable here is that backup connection that for the failover purposes. So in the normal running case was that, and then let's consider the case when a head node goes down, right? Let's say the head node connecting to the top tree goes down, right? And then you could issue a MRPC command from this head node. Firstly, unband SSDs from this partition, and then band the SSD to partition 1. Okay, and in this case, the 30 SSDs will be hot add to this head node, and then you are now losing the data because the data can still be serviced from this head node as well. That's basically how we handle the failover situation. And when this guy's got repaired or boots up, you can issue another unband command to disconnect the SSDs from this partition and reconnect it to here, right? This is the failover case. Okay, so I think I touched upon the potential use cases. We feel this is mostly more useful than applying head node downtime. Let's say if you're doing kernel upgrades, right? If you're doing a kernel upgrades, if you're doing a maintenance on the head nodes, you're for sure going to reboot the head nodes, and the data is not going to be available for an extended period of time. And you could, instead of doing that, you can fail over the SSD to the other head nodes and make the data still available, perform the maintenance, and then be back online after you finish. This is one use case. And the other use case is really what we call the unplanned head node downtime. If you really have a head node failure, like a CPU failure, memory failure, or a flow failure that you need to repair, Or if you only simply have a kernel panic, Linux operating system goes down, and this is the time you could use the head node downtime, the unplanned. This is what we call unplanned head node downtime, and this you could certainly take advantage of a failover capability here. Okay, so some conclusions. We explored different configuration options based on basically the workload's needs. It's really about how the application consume the CPU and memory, and be able to provide the right flash capacity to that host, so that we are not wasting any flash capacity. Right? We also discussed how we actually improve the system reliability by creating a failover scenario. So Lightning, again, it's a very flexible platform to be able to fulfill those needs, different needs. So if you're looking at adopting Lightning in your environment, it would be great if you explore these options, and these configurations hopefully help you to make the best choice. And lastly, I want to mention, I really work closely with our ODMs on these features. We even their firmware team helped me run through all these configurations, validate the concepts, and do a lot of testing, validations to make sure they're working, right? So if you plan to adopt, you can also talk to the ODM team as well, and learn from what we have done to enable these configurations. And so does engineers from Microchip, and they also help me to understand how the switch should be configured. And just feel free to reach out me and the ODMs and the switch companies. And lastly, I want to really mention one thing is what I present here is really the hardware aspect of the entire system, right? The hardware support failover capability, but there's especially for the failover case, there's a lot of software involvement, intelligence need to build in to be able to identify this is a failover situation, and then automatically take over the SSD for the still surviving head node, and be able to take over the SSD in a way that is not causing the NVMe timeout, not causing the I/O timeouts is also critical. These are really the software aspects of the complexity. But I don't want to just cover the hardware here. I want to mention the software is non-trivial. And with that, thank you very much. If you have any questions, thank you.